So you're on your swing set, and you're twisting around so that you can eventually let it go and start spinning. You at some level know the torsional properties of that swing set. At some level, you know that it requires more force to twist it a full turn than it does to twist it a half a turn. You know the twisting or the torsional properties of that swing set. Coulomb used the same principle to measure the electric force between two charges. Here's the setup. We have a string hanging from something, and on the end of that string we have a rod, and on the end of that rod we have two objects right here. One of those objects is charged. We'll call it Q1. The other one doesn't matter. We have Q1 and then we have something else, whatever, just there for symmetry. Now we bring another object Q2 nearby it, and there's going to be a force of either attraction or repulsion between these two charges. One will either attract number 2 towards it or to repel number 2 away from it. It doesn't really matter, but the attraction or repulsion is based on either opposite charges or like charges. But in the end, it doesn't matter which way this charge number 1 goes, toward or away from number 2, because in the end, we want to measure the amount of twisting of the string. How much it twists. Did it twist 3 degrees? Did it twist 90 degrees and go a quarter of a turn around? Or did it go all the way around once and twist 360 degrees? Actually, it wouldn't go that far. That would mess up the whole experiment if it went that far. But you get the idea. We measure the amount that it twists, and then from that we deduce the amount of electric force, the force of repulsion or attraction. We can also measure the distance that separates them really, really easily. We'll call that R. Just use a ruler or something like a ruler to do that. And finally, the charges, Q1 and Q2. Well, we can't measure those directly, or at least in Coulomb's time we couldn't measure those directly, but we can, or he could, deduce what charge was relative to what it was. In other words, if he has a charge of Q, touches it against something that's neutral, it becomes a half Q. Well, then touch it against neutral again, it becomes a quarter Q. Touch it against neutral again, it becomes an eighth Q, and so on. So he's able to change the value of Q1 and Q2 without really knowing what the values are, but just comparing it to what the values were. Question? So here's what Coulomb does. 3 experiments to try to determine the relationship between F, R, Q1, and Q2. The first experiment, he manipulates the value of Q1, and he finds the value of F in response to that. So manipulated variable, responding variable. What would be my control variables there? What do I got to keep constant in this experiment? If I'm changing Q1 and F is responding to that, then I better keep Q2 constant. And I also better keep the distance that separates them constant. So I'm going to make my control variables Q2, and I'm going to make my other one R. And then I'm going to plot a graph of responding versus manipulated variable, F versus R. And when I do that, I get a straight line. The relationship that Coulomb deduces from that is this one. F is related to, that shouldn't be R, that should be Q1. F is directly related to Q1. In other words, whatever happens to Q1 happens to F. As Q1 goes up, F goes up as well. Now, the second experiment he does relates Q2 to F. Manipulate Q2, see how F responds to that, controls Q1 and R. Plots a graph, F versus Q2. Sure enough, he gets a straight line for that one as well. Tells him the relationship is linear again. F is related to Q2, directly related to Q2. And then finally, he manipulates R, see how F responds to that. My control variables in this case would be what? What and what? What and what? Mason, what are my control variables here? Good, Q1 and Q2. Plots a graph. And this time, he gets a graph that looks like this. Now, this could be a few different relationships, but the one that this graph, this particular data is this one. F is related to 1 over R squared. So now he's got 3 relationships, F in Q1, F in Q2, and F and R. Now what he wants to do is put them together. If he says F is related to Q1, and it's related to Q2, and it's related to 1 over R squared, then my relationship is F is related to Q1, Q2 over R squared. But just like yesterday, we said when Y is related to X, Y is equal to the slope times X, the slope being a constant. We want to make an equation out of this. We need a constant. So F, or Y, is equal to a constant, or this time we'll call it K rather than M, times Q1, Q2 over R squared. That's our equation that finds the electric force that acts between two charges. K, by the way, has a value of 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. And this should look familiar to us, right? What equation from Physics 20 looks a lot like this? Gravitational force, right? Newton's law of universal gravitation. It's this one. F is equal to big G, M1, M2 over R squared. G has a value much smaller, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. What do these two equations have in common? Well, the basic structure of the equation. They're both what we call inverse square equations. Why? Because the force is inversely related to the square of the distance. What's different about them? Well, one uses mass, one uses charge, right? That's a pretty big difference. What else is different about them? Well, the direction. Sorry, go ahead. You going to answer one? Okay. We'll talk about that in a second. The direction is different. Gravity is always attractive. Electric force can be attractive or repulsive. Anybody know why gravity can only be attractive? Why you can't have attraction and repulsion with gravity? Yeah. You have two types of charge, positive and negative. Two types of charge that are the same give you a repulsive force. Two opposite charges give you an attractive force. You can't have two different masses, right? They're all the same. So it's got to always produce the same type of force. And it happens to be an attractive force. Jack, what did you say?
The bottom one uses G.
Okay, so the bottom one uses G, which is a much smaller number than K, right? Which leads us to gravitational force being a weaker force than the electric force. The electric force is stronger by a long shot than the gravitational force. As much as sometimes we think gravity is such a big force, it really isn't. Of the four fundamental forces, it's the weakest one. Okay, the electrostatic force is pretty large compared to that. Make sense? Okay, let's take a look at a problem here. Example number 1. This is in the booklet that you got earlier. It says a metal sphere with a positive charge of 5.5 and a mass of 2.5 is separated from an identical metal sphere with a negative charge of 2.0 times 10 to the minus 7 and by a distance of 5 centimeters. I'm going to circle a couple things. The centimeters, the fact that this is positive, and the fact that this is negative. Draw attention to anything that could lead me to a mistake. Determine the electric force on the positive charge and the electric force on the negative charge, and then the acceleration. Let's write down some givens here. We've got Q1. We're going to make it positive 5.50 times 10 to the negative 7 coulombs. Q2, we're going to make negative 2.00 times 10 to the negative 7 coulombs. And we're going to make mass 1 2.50 times 10 to the negative 3 kilograms. The distance that separates these two charges, 5 centimeters, 0.050 meters. And we're going to find the electric force on the positive and on the negative. How do I find two different forces with this equation? Listen carefully to what I'm about to say. Regardless of the charge on charge A and the charge on charge B, regardless of the mass on charge A and the mass on charge B, A could have way more charge, or as in this case, in this case it does have way more charge than charge B, or B could have way more charge than charge A, or they could be the same charge. A could be heavier, A could be lighter. It doesn't matter. The force on A, the force that A applies on B is equal and opposite to the force that B applies on A every time. So if we solve for the force here using KQ1, Q2 over R squared, we found both of them. Does that make sense? We don't need to find two forces. Okay, the force between A and B is the same regardless of which one you're finding it for. So let's just find F and not worry about trying to find it for one particular charge or the other. KQ1, Q2 over R squared. We got 8.99 times 10 to the 9 times Q1, which I said is 5.5 times 10 to the minus 7. By the way, it doesn't matter which one's which. 2 times 10 to the negative 7 divided by R squared, which is 0.0500 squared. Is that okay, or is there a mistake there? Am I missing anything? Yeah, Jade?
The radius 0.005?
No, 5 centimeters is 5 divided by 100, which is 0.05. No, that part of it's right. Yep. Shouldn't you make 2.0 times 10 to the negative 7 negative? Well, it is a negative charge, but listen carefully to this. I don't want you to ever sub the sign of a charge into an equation. Got it? Leave it like it is. We have to pay attention to signs sometimes. We have to know whether they're positive or negative for other reasons, like to see if they attract or repel. In this case, because they're positive and negative, they would attract each other. But in the equation, we don't want to do that. We don't ever want to start plugging signs of charge into an equation. Here's why. For us, signs mean left, right, up, down. They mean direction. When we sub a sign into an equation, we want it to mean direction. We don't want it to mean a type of something. We're going to start mixing and matching two different sign conventions if we start putting a negative in for that charge. So just don't do it for this equation or any other equation. We're going to do the math here, by the way. We get 3.9556 times 10 to the minus 1 newtons, which rounds to two digits right there. Actually, it would be 4.0, wouldn't it? To two digits, that's a 5 or bigger, so we'd round it to 4.0 times 10 to the negative 1 newtons. There's my force. And that's the force on both of them, right? What about the acceleration? This is new. We haven't found an acceleration yet in Physics 30. It's new, but it's kind of easy. Why don't we just say A is equal to F over M? Whenever you want to find an acceleration in Physics 30, here's what I want you to do. Get a force, whether it's an electric force or a magnetic force or whatever force it is that we're talking about. Get a force and then divide it by mass. The force, this A is equal to F over M is like Jedi Academy. The force needs to be with you. But then you go learn what to do with the force. Okay, A is equal to F over M is doing something with the force. The force needs to be with you. And you're going to get the force by using KQ1, Q2 over R squared in this case, or by some other way in some other context. But once you have the force, in just about every case in Physics 30, when you're looking for the acceleration, you're just going to say A is equal to F over M. Make sense? May the force be with you. Then say A is equal to F over M. That's up on the back side, the back sheet there under the always list. You want to find acceleration? May the force be with you. And then A is equal to F over M. Hey, the force is with us. Now we'll do our little Jedi training, learn what to do with the force, and say F over M gives me the acceleration. I get 1.6 times 10 to the 2 meters per second squared. Make sense? That should be automatic to us in physics 30 from here on out. You want the acceleration? Okay, get the force. Whatever type of force it is, get the force. And then divide it by the mass. All right, one more example before we call it a day. This question says the two spheres in the previous example are momentarily touched together, then separated by the original distance, separation distance of 5 centimeters again. What's the electric force that acts between the two charges? Isn't this the same question? It's the same two charges. Right, we get the same two charges, we touch them, but then we move them back to where they were before, 5 centimeters. Isn't the force going to be the same? Why is the force not the same? Pardon me? No, distance is the same. It was 5 centimeters in the last question, still 5 centimeters. Yeah? Yeah, I touched them together. And when I touched them together, what did they do? Conduction, yeah, they charged by conduction and balanced out, right? So the charges were 5.5 and negative 2. Now the charges are going to balance out to be, well, let's figure that out. 5.5 times 10 to the negative 7 plus negative 2 times 10 to the negative 7 over 2. The charges are going to balance out to be 1.75 times 10 to the negative 7 coulombs. So that's what the charges are now. Then I've got to figure out what the force is. It's KQ1, Q2 over R squared, or 8.99 times 10 to the 9 times Q1, which is 1.75 times 10 to the negative 7. Now it is. It wasn't before, but now it is. Times 1.75 times 10 to the negative 7. Was negative 2 times 10 to the negative 7, but now it's 1.75. Divided by R, which is 0.050 squared. And we solve for this force, we get 0.110 newtons. So in the last one, we got 0.40 newtons. This one, we got 0.11 newtons. Different force. It's different charges. Even though it's the same objects, they're charged differently now. Right? Okay, here's your homework for tonight.